Hello, my name is Ian Woodbrook, and I'm doing my independent studies project on rocketry and its history, aerodynamics and its history, and ballistics. My project included many different things for learning, including researching for an essay, doing an interview with a missile technician named Joshua Titherington, and launching off a rocket that I built. Now we're going to talk about rockets and their different uses. They have tons of uses, from science to warfare. The first one we're going to talk about is a science use called a sounding rocket.
Shown here is a sounding rocket from Johns Hopkins University. It is used to take atmospheric measurements for scientific experiments. They are also used for human transportation from the earliest days of the space program. These tests eventually resulted in human spaceflight, culminating in the manned lunar landings.
Rockets have a long history, starting with the Chinese, where they invented black powder.
They would attach small rockets to arrows and then launch them at their enemies.
When the Mongols attacked China and saw their use of rockets, they were like, whoa, we need to get some of these for ourselves. And then they attacked Europe. Europe, unfortunately, did not learn of rockets at the time and were just hiding out in their castles. But India, after a while, learned about rockets, and when Europe was fighting India, they picked up rockets from them.
William Congreve invented the Congreve rocket for the Europeans. It was a great weapon, but it was very inaccurate, and you could even hit your own side when using it in the army.
So eventually, a guy took this rocket and they decided to make it spin in flight, making it much more accurate and a better rocket. Now we're going to talk about aerodynamics. The principles of aerodynamics are how air affects an object in flight.
There are 4 basic forces in aerodynamics: weight, drag, thrust, and lift. For many ballistic rockets, lift is 0 because it requires some form of wing interacting with the air. Thrust is the amount of push caused by the fuel being burned. Drag is air resistance that slows the rocket and opposes thrust. And weight is the effective gravity and also opposes thrust in this model, but opposes lift on an airframe using wings to provide lift.
Now we're going to talk about the history of aerodynamics. The principles of aerodynamics have been known to man since the first caveman threw a rock. But they actually began being studied in ancient Greece by a philosopher called Aristotle. Aristotle began to think about the laws of aerodynamics, and he was thinking about how an object moves through an air and the forces that act upon it. But he and a later philosopher on aerodynamics called Archimedes didn't get very far because it was still a basic concept at that time. Our last topic is ballistics. Ballistics studies the flight trajectory of a rocket. Certain things in ballistics will take a rocket and it will actually change the trajectory. And that's why we have ballistic calculations. Ballistic calculations depend on gravity, air drag, really anything that will affect the flight of the rocket. Ballistics says where the point of impact is based on how it's launched, and the weather conditions will affect it. So basically, the lighter the rocket is, the less stable it is, the more ballistic calculations it would require. But the heavier the rocket, the more stable it is. It's a little bit simpler launching it. Ballistics is affected by the density of the atmosphere, but is also effective in a no gravity and no atmosphere environment because it is still based on the thrust coming out of the rocket. What is your job?
So my relationship to rockets and missiles was that I was a missile technician in the Navy. I worked on the NATO Sea Sparrow missile system, as well as the rolling airframe missile system. So primarily I was NATO Sea Sparrow. And then I also worked on the radar system that was attached to that.
What's your experience as far as the vectoring devices and how you work with them?
The vectoring devices, all the devices used to turn the missile. So I've got some different, I've got two specific experience with that. The first one was with our first version of the missile that we used, which is the RIM 7. And on that, we would have fins, which were separate. When the missile is delivered, the missile itself is separate from the fins. And so as we're loading and raising the missile into the launcher, we would pause halfway through and attach these fins. There would be 2 on the top and 2 on the bottom. So 4 fins total. In some cases, I believe they're also in the front, but I believe in this case they were about in the middle of the missile. So guidance and vector control are 2 separate things. Guidance is the steering wheel, and then vector control would be the tires. It worked very well, but what made it not work very well was the system that was designed to turn the missile, which is called an open loop hydraulic system. And what that is a system in which fluid is used to change the angle of the fins. The problem with that is that every time the fluid was used to move the fins, fluid would squirt out the back. So every time fluid moved, you would lose a little bit. You may have 6 to, if you're lucky, 8 turns out of it before the fins would lock in wherever vector they were in, and that is the flight path it would continue on. There is another way that we use to turn our missile, and that was thrust vectoring. And what that means is the thruster itself had the ability to move. And so there were no fins there are fins still, but they don't turn it. They're just a stabilizing device. It was theorized that if we needed to launch a missile from one side of the ship and have it go over the flight deck to the other, we could have the missile pop out and then launch straight up and then go over the flight deck. And that type of vectoring, thrust vectoring, makes that possible.